Good morning, y'all.
Hey, good morning.
How are the people in the neighborhood?
I'm doing good. How are you?
I'm great. Thank you for asking, Raymond. Let's see, I want to throw one thing in. Add to this class really quick. Moment of a force around 0.1314. Yeah, that's that. All right. See if we learned anything from yesterday and whether the dot product is our friend. All right. Okay, so let's play with the dot product just a hair more. And projection and so forth. So anyway, let's see if we can visualize this. So we took off yesterday, just kind of quickly looking at what a projection was. So we said the projection of, actually, let's just copy this out of the note sheet so that it makes you used to what you're usually looking at. This guy, the projection. So that you get used to it for a test. Because this section is pretty formula heavy, so you want to feel good about that part of it. Not realize what you have to memorize and what you don't. So, anything bugging you about that particular formula?
The law of cosines one.
Not the dot product. Actually, we'll do an example of that too in just a second. But really, this projection business. So we said that yesterday that this kind of conceptually we were able to maybe understand what this was doing. But given that it required us to know the angle, which kind of makes the problem a little more complicated, we built ultimately this formula yesterday. So it's really those two things that are equal. So again, let's see if we can do this. Again, that's pronounced or described as the projection of u onto vector v. In other words, what part of vector u is actually pointing toward v. We said yesterday, just so that you kind of walk away getting this. If I put vector u over here somewhere, kind of heading up in that direction, then ultimately if I project straight down, and this 90-degree angle thing is kind of neat, then that right there is basically the portion of u that's actually projected onto v. And so, as I said yesterday, that's important that you understand the order of that. That's the projection of u onto V, the portion of U that's going in the same direction. Anyway, I give you a couple illustrations, but let's try this in a 3D component or
Oh, we
context.
can't see your iPad, by the way.
Oh, you can't?
No. At least I can't. I don't know if anyone else can. It's like stuck on the unlock screen.
I thought I was the only one that came in late.
I'll try sharing again. It's looking good from my end, but I did just fire up a new computer this morning, so. What do you see now?
Yeah, that's better.
It is? Okay. So the important thing to understand about what the projection of U onto V is that if U is up here, the projection of U down onto V is this little vector right here, hitting down there at kind of 90 degrees. So it's making a right triangle. And we said yesterday, that's why this works. In other words, if this angle right here is theta, then whatever the magnitude of U is, let's say that's 10. Well, if you take 10 times the cosine of theta, isn't that what this length is down here? That would be the length. But we're interested in not just the length, but also what direction does it go? And so in a sense, we said this took care of kind of the direction it went. This was the length or size, it was wind, miles per hour, that kind of a thing. And as an illustration, this was kind of the important part. So if this was the airplane flying, if you will, and they're flying in this direction, it's got kind of this wind blowing in this direction over here at say 10 miles an hour, the wind is behind us. And so that would represent a tailwind. Well, how much of that, 10 miles per hour is actually in the same direction we're going? Because that's the only part of that 10 that's actually going to make any difference. And if you take 10, just for the heck of it, 10 times the cosine of, I don't know, that angle looks like about 50 degrees, you get 6.4. So that means 6.4 miles per hour of that 10 is actually helping your airplane fly faster, if you will. And so that's kind of the application for this, or kind of the logic as to how you want to think about this. So that 6.4 would take care of the length of the vector. Remember, length is representative of all kinds of things like force and miles per hour and all kinds of quantities. And then direction is ultimately determined by, getting it to go in the direction of V. And then we just said, hey, that's cool. But, what we have kind of in the blue boxes represents a shortcut. So what if I said U is, and I think I'll write it in, well, I think I'll write it in this form this time. 5I minus 2J plus 6K. So that's a way of telling you X, Y, and Z. And no one's going to be an idiot and kind of rearrange those. In a sense, the first number is X, the second number is Y, the third number is the Z component. But the letters do help you keep that straight. And the idea is for, if you were adding these vectors or something, you'd be making sure to add the I's with the I's and the J's with the J's and so forth. So let's see, let's make this 4I plus 3J minus 5K. So can you find the projection of U onto V from those two vectors? I'm going to give you a second to write that down, and I'm going to go try to draw this in GeoGebra. 5, 2, 6. Four, 3, -5. All right, so the recipe, the things it calls for over there is U dot V dot product. We said that was a mnemonic device yesterday. You, again, it's a good habit to get into to draw the vector symbol on the top of it. So 4 times 5 is 20, 3 times 2 is -6, 5 times -5 times 6 is -30. So you have -36 and 20, which is -16. So there's our dot product. And then we have to find the magnitude of vector V squared. And so that'd be 4 squared plus 3 squared plus 5 squared, which is 50. And normally I would square root it to find the magnitude, but again, this is squared, so that's actually 50. So what we said yesterday was that just represents your multiplier. So your multiplier then for the projection of U1, 2, V has the multiplier -16/50, and that's just multiplied by vector V. Which I'll write this way. And so if we haven't blown it, then again, I'm gonna write these as, I think I'll write them as decimals. Since 50 is such a nice denominator, we're gonna get reasonable decimals here. So 64 divided by 50 is 1.28. And 48 divided by 50 is -0.96. Let's see, 5 divided by 50 is 10. So that'd be 1.6. And negative times a negative is a positive. So we think this is the correct answer. We think. But the issue is, does it look like, well, this picture up here? I mean, does the vector that we just described actually cruise right along vector V, meaning it got the direction right? And would it be dropped down? If we dropped it down, would it really kind of look perpendicular if we kind of shoot it straight down to vector V? And so let's take a look. So I got the other two vectors drawn in GeoGebra. So let's just add this last one. Let's see, I'm just assuming I can get away with calling it W. As I mentioned yesterday, I'm getting away with typing this kind of as an ordered pair, which is kind of cool. So we said -1.28 and -0.96 and +1.6. And close the parentheses, boom, and we think we're done. So the question is, are we? So vector U is the green one, so it's projected down onto V. And notice that like our W vector kind of looks right, except for, I think I'll make it yellow, probably will stand out. It's like going the wrong direction, which is kind of cool to see because it means I made a mistake. It's actually going the, I don't know if you stare at it, would you agree it's aiming the same direction as vector V, but it's kind of going backwards. Is that right? Is that wrong or is that right? Did I make a mistake or do you think this looks correct? And personally, I'm actually more interested in your conceptual understanding of what you just did rather than all you did is adding and subtracting and multiplying and dividing, right? So does that look right?
Based on my idea of like the pictures you drawn, I thought it was going to lay directly on the V, vector V.
Yeah, I thought it was going to be aim in the same direction as the black vector, didn't you? My first thought was that it was wrong. Now I'm actually thinking it's right. What do you
Do
think?
we need to flip some of the negative signs? I don't know if that would fix it.
Yeah, my first thought was the negative signs are backwards. You know, I got like accidentally lost a negative sign or something kind of goofy like that. I'm trying to flip this around to a good direction to see this, but I can't get it where I want it.
Well, since the green vector is pointing in the opposite direction, it might make sense that our projection is actually going the other way.
Yeah. Let me get it over here where we can draw on it a little bit. So my first instinct was that it's not right, but in the end, this kind of, I think, came up as a kind of a good example because it kind of isn't facing the right way, or at least the way that we thought it would. But let's stare at that for just a second. So if that's vector U and this is vector V, and that's our projection. Well, didn't we say a second ago that it had to go straight down to vector V and hit it at 90 degrees? Well, notice this angle right here is greater than 90 degrees in this case. So if that's the case, it's actually kind of projecting the other direction. Now think of this as an airplane. So this is the airplane, this is the plane, and this is the wind up here. Is the wind a headwind or a tailwind in this case? So it's blowing you off course for sure, but is it actually slowing you down or is it speeding you up? You understand that question? Well, because that angle is more than 90 degrees, just redrawing this to make it more accurate. First of all, I think that looks like 90 degrees. That's a good sign. But because that's more than 90 degrees, the wind is actually blowing in your face a little bit. Does that make sense? It's actually slowing you down. Well, that's exactly what that yellow vector represents. In other words, whatever the length of that vector is, maybe, you know, the wind here is a really big vector, like the length of U and the length of V are almost the same. This is like a massive wind. But the yellow vector represents the part of it that's going the same direction. Well, in this case, it's actually in your face a little bit. So it's a headwind. So it'd actually be slowing you down. So I guess we can't just kind of always say, you know, that this is behind us or, you know, the wind is behind us here. I mean, wouldn't it be possible if I go back up here and just kind of draw another one really quick? If I said this was vector V, right here, isn't it possible that vector u would go in this direction? In which case, if I dropped it down to right there, wouldn't that be backwards? I guess that is possible, the projection of u onto v. That'd be possible for it to go backwards. In other words, it's hurting you, not helping you, that kind of a thing. It's pulling in the opposite direction. So I guess it doesn't just have to line on it and help. It could land on it and actually go in the reverse direction. So the things about this that look correct is, notice when I redrew that red line, as I mentioned a second ago, like that really does look like 90 degrees. It should. And that does, and therefore that makes me think I got it right. The other thing is, well, you know, this is lined up. It's pointing in the same exact direction. It's pointing negatively. And let's stare at that for just a second. Notice the units for our vector up here, our v vector. This was a positive and then a negative. But what happened to our projection vector? It was a negative, and a positive. In other words, exactly the opposite signs, which means it's going in exactly the opposite direction. And in this case, that actually makes sense. So I don't think it's wrong after all. Now, just for the heck of it real quick, since this is one of the cool questions we can answer, like, could you also come back here and calculate what that angle is in 3D? We did this yesterday, but since we're just staring at this cool example, in other words, I said it's more than 90, well, why not figure out what it is? And that's effectively this note from yesterday, the one that does have theta involved. So I mean, there's more than one way to write this formula down, but you know what, the way I wrote it in class is the cosine of theta is the dot product divided by the magnitude of the two vectors, and then I can take inverse cosine. So do you get something more than 90 real quick, and then we'll. So you should notice we already figured out most of those things in the previous problem. We know the dot product was negative 16. We know the magnitude of V was the square root of 50. So the only thing we really don't know is the magnitude of U. Since U is 5, 2, and 6, square those, add them together, you get 65. And so the magnitude of U is the square root of 65. So the usual way this is written down is the cosine of theta is the dot product divided by those two scalar values, those two numerical values. So I'm typing inverse cosine of negative 16 divided by the square root of 50 divided by the square root of 65 as we did yesterday. And I got happily that theta is indeed, as the picture would have indicated, more than 90. I got 105, 106.3 degrees. So that doesn't prove I didn't make a math mistake, but at least I got what the picture would have indicated, something a little bit bigger than that.
Real quick, so that one form of the equation, the magnitude of u times cosine of v divided by the magnitude of v, would you do the cosine on each component of v divided by the magnitude of v? Or am I misunderstanding the notation?
I'm not totally sure. But this is what I just typed in. I typed the inverse cosine of, and I just typed -16 divided by -50 divided by the square root of 50. That's what I typed in my calculator, because no, that's just a number over there. In other words, if you figured out what number 16 over the square root of 50 and so forth is, I'm going to do that really quick. I think that number is actually approximately -0.28. And remember, the cosine of an angle can't be bigger than 1. In other words, it's somewhere between 1 and -1. So the fact that that came out to be something between 1 and -1 means it's an answer. So it's really just the inverse cosine of -0.28. But I'm not sure I answered your question, Cheyenne, did I?
No, I was actually, if you go back to the formula sheet, it was closer to the top.
The projection one, or
Yeah.
the full
Yeah, the
sheet?
projection one, where you have the vector v divided by the magnitude of v.
Got it.
Would that be the entire each x, y, z component divided by the magnitude?
Yeah, that's exactly right. In other words, vector v was 4, 3, -5. And since we just found out, a minute ago, that the magnitude was the square root of 50. Remember, what are you doing? What are you doing when you take a vector like 4, 3, -5 and you say, I think I'm going to multiply that by something? Let's just stop and think about that for a second. So just in a example, just kind of a separate problem down here. Let's do this 2D so that we don't get confused. So if I say vector A is equal to 2, 3. When I decide, I think I'm going to double that. I'm going to double that vector, which really just means I'm going to multiply both of them. It's kind of distributable. I'm going to multiply by 6. What are those two vectors? What just happened? Went black for a second. What do those two vectors just look like? Well, if I go over 2 and up 3, then I'm going to get that vector for A. What's vector 2A going to look like?
It'll just be bigger, but the same direction.
Exactly. So the important thing is that it's the same direction. So I'm going to go over 4, up 6, and it's going to land right there. And so vector V, or vector 2A, is exactly the same direction, but double the length. Well, think about what we're doing up here. We're taking this vector 4, 3, -5, which, by the way, has a length of the square root. This was the one that was the square root of 50, right? The square root of 50, which as a decimal is like 7, right? A little over 7. So it has a length of 7. Well, if we take that vector and we say, I'm going to multiply it by 1 over the square root of 50, what's that going to do? It's going to make it shorter. instead of being longer, it's going to be shorter. And the cool thing about what that does is, what is its length? So it's shorter, fine, but what's its length? Well, because we're actually dividing by the magnitude, the length of this new vector is going to be 1, which is really cool, because if that represents miles per hour, then when I'm trying to change the direction of something, I don't want to change its size. This length over here already was the miles per hour, and I don't want to screw that up. And so what I want to do is take the 4, 3, -5, which actually has a distance of 7. Remember, in our context, that'd be like 7 miles per hour. Well, I don't want 7 miles per hour multiplied by this. I want to multiply by 1. And so when we effectively divide by the magnitude, we're changing that directional vector to be a unit vector, which means length 1. This whole thing is the length. The length equals 1 version of vector v. And now when I go multiply it by the length that represented the miles per hour of the wind, which is going to make it bigger again, then I'm getting both the correct direction and the right length. Does that make sense?
Yeah, that makes sense.
Now, here's one. Let's do that again. So here's one side benefit to this, or kind of a, I don't know if I want to say application, but I'll just mention this. If I say application again in quotes for the dot product. So we talked about, how it finds the angle between the two vectors, but one of the things that's really, I don't know, kind of useful, I guess, is the concept of perpendicular. In other words, two vectors that are 90 degrees to each other and so forth. That's a very interesting situation. Well, we were just using that, right, when we did this projection business. There's a situation where we really needed to understand perpendicular well, so that we got that correct, so that we sort of adjusted the wind to be the correct size. And so anyway, I'll show you a number of examples down the road of things that are perpendicular. But let's just think about perpendicular for a second. What would cause that? Well, if the cosine of theta equals the dot product of these two vectors divided by their magnitudes, what would happen in the event that we were perpendicular? Well, perpendicular is when that angle is 90 degrees, right? But what's the cosine of 90 degrees? Think unit circle. I hope you don't have that memorized. I hope you actually have to draw a picture in your mind's eye and think, okay, SOHCAHTOA, cosine is x. X at 90 degrees, it'd be 0. Cosine of 90 would be 0. So perpendicular, the cosine of 90, that'd be 0. Well, when is this equal to 0? Notice that's a very unique answer. And we spent a lot of time with this, recently on the whole vertical slopes, and when a slope had a fraction like this, we have a fractional equation here. Well, when that's equal to 0 is just when the top is equal to 0. So does it make sense that it's perpendicular when u dot v is equal to 0? In a sense, like it's like a shortcut, if you will. For the most part, you're just gonna, it'll be like the random problems I made up. Like if it was wind and an airplane or something, it's like, the chances of those being perpendicular are really slim. If I say, what's the angle between these, and I make them up, it's never going to be 90. It's like you'd have to work at this. But notice, if the dot product is 0, then that means the cosine of theta would have to be 0. And the only way that happens is at 90. Or I guess you could say 270, right? But either way, that's perpendicular, right? So interesting. So let me see here. I'm going to try to make one up that does this. Let's see, 2 times 2 times 3 would be 6. And 6 times 1 would be 6. So those are both 6 now. And all I got to do is kind of make one negative. So you agree that those would have to be perpendicular then, I guess? I want you to think about this in light of like how you may remember the way that you made lines perpendicular based on slope. Think about that. Think about that back in the day when you were looking at equations of lines and you said, you know, what's perpendicular to that? That slope's 2/3, you know, what's a perpendicular slope to 2/3? And you may remember, like, what do you do about that? Well, think about that in light of this. So if I graph this thing, I might as well graph it accurately. So there's 2, 6. Just want to see it. Some things in life are hard, but they don't need to be hard if we don't want them to be. There's 3, 1, 3, -1. Sure enough, if that's U and that's V, they really do look perpendicular. Cool. How did that work for slope? I just kind of sparked your memory, perhaps. If we have a slope of 2/3 back in line world, what did you do to get the perpendicular slope? What did you do to that fraction?
Multiplied by like the negative inverse.
Yeah. So you invert it, flip it upside down, and then if it used to be positive, now it's negative. So mathematicians would say inverse reciprocal. Reciprocal is flip, inverse is change the sign. Normal humans would say flip it, change the sign. So you know, is that related here? Is that kind of related to what you're seeing in this case? I mean, think about the slope of 2, 6, and 3, -1. For you, what we've been noticing is that, you know, if X is 2 and Y is 6, I mean, isn't the slope of this 6/2? Rise over run? And isn't the slope of this similarly Y/X? We notice that works here. I mean, it's actually related to something that you knew before, I guess is all I'm saying. This isn't actually as brand new as it might appear. But in the case of slope, we call them rise and run, whereas in the case of vectors, we call them X and Y. But effectively, what are you doing here? Well, you're taking X times X. So that's this number times this number. That's what a dot product is doing. So if I take numerators and multiply them together, and then I take denominators, then I take the numerators and multiply them together, and I add those, I'm going to get 0. This is all kind of tied together. Anyway, that's just kind of cool. So it's actually possible to tell if 2 vectors are perpendicular. It's possible to make 2 vectors that are perpendicular based on this. And I won't take the time to kind of go 3D with this, but that, you know, the same thing would apply in 3D. Okay, so I think we've beat the dot product to death. And we've applied it to a projection. We've got a note sheet on it. We have a sense of how that works. And that's one of the, like, that's how you multiply in vector world. If you want to multiply 2 vectors, this is how you do it. And now let's take a look at something else. As it turns out, let's see, what section is that? 13.4. let's spend a little time on the intro to something called the cross product. So I just got done telling you that the dot product is how you multiply vectors. Well, it actually turns out there's two ways to multiply vectors and they accomplish two different tasks. Simply put, the dot product was a mnemonic device that allows you to find the angle between a couple of vectors, because that's something that's rather interesting to know. As I said, it would affect kind of how hard, how far things are pulling. We won't do this, but just as an example, if you had a tugboat over here pulling with, say, 2,200 pounds pulling in that direction, and then you had another tugboat attached over here to your whatever garbage barge or whatever it is you're pulling along in the water, and this was more, we'll say this is 2,800 pounds of force. Does it make sense you would need to know what direction that was going to actually go? Or if these were, joints on a bridge, I need to know the result of that. I mean, that's what finding this angle right here is kind of a big part of that. And that's what a dot product will do for you. But what does a cross product do? So there's actually a whole second way, if you will, to multiply vectors. And similarly, it's just a mnemonic device. And I want to try to kind of help you understand what a cross product does, what it accomplishes in the form of an illustration. So,
Man, we can unblock the Suez Canal with this.
exactly. I saw this engineering video one time where this is amazing. They, I think they were Swiss engineers had built this drilling rigs. They're drilling for oil in the ocean. Well, that's really tough to do because ocean is caustic on things, and also you have storms, and it was actually in the North Sea. And so what they effectively did is built like a kind of a boat that was like a concrete walls all the way down to the bottom, and the goal was basically just to go sink this thing in the ocean so that you just had a tunnel to the bottom of the ocean floor and you didn't have to actually contact the ocean at all, just kind of drill kind of right through the bottom, and then you could actually bring it so people could actually walk down to the bottom, and you don't have all the scuba issues with with breathing compressed air and those kinds of things. And but the long and the short of it was they built this thing in an inlet where there wasn't much wind, and basically by filling it with water they could get it to sink, and because it was made of concrete. But if they pumped all the water out, it would float like a boat. And so they got it all built, and then they pumped a lot of the water out, not all of it, because then it would kind of want to tip over, but they pumped a lot of the water out, and then they did exactly what I just showed, except for they had like 7 tugboats hooked to it because it was really heavy, and once you get it moving, it doesn't want to stop easily. And so they had, in a sense, tugboats were going in every direction in a star pattern. Most of them were, if you will, kind of pulling in the same direction, trying to get it out to sea. But then they had like a couple of them over here kind of pulling this way to help kind of steer it. But it's interesting because you're on the radio and somebody's trying to dictate what to do. But anyway, that's kind of what this is about, is like what how do you figure out all those vector forces in pounds pulling on this thing in every direction, and how do you reconcile all that and know what's going to happen? I mean, that's the math that we're studying right now. So what's a cross product? So the application for a dot product is finding an angle. That's kind of the best way to conceptualize what it's doing. It's a mnemonic device to find the angle. And I think I'll just tell you right up front, this is a mnemonic technique invented to find torque, or as engineers call it, moment. Now, as an extra credit question, I'm reasonably sure what I just told you is true. I said it was invented to do this. Is that true? Sometimes mathematicians find beautiful mathematics, and it's only kind of later that people discover uses for it. I'm relatively sure this is true. I'm relatively sure this is the reason for it. We saw that there was, kind of 2 uses for a dot product. It allowed us to project one vector onto another and find the angle between them. It's like a couple of uses, and this one has a couple of uses too, but I'm relatively sure this is the primary one. But again, I find this stuff interesting. Invented to find torque. Oh, it was invented by who, when, where, you know? Is that really why? Maybe that's lost to antiquity, but maybe not. Anyway, you probably know how torque works a little bit. So here's the classic example. So you've got this nut that you want to get off, and so you put a wrench on the top of this. And then you push. So if you don't learn anything else today, are you tightening that nut or loosening that nut?
Loosening.
Loosening, righty tighty, lefty loosey. You're loosening this thing. And so sometimes it's like, man, that won't go. I don't know if you've ever had that opportunity, but it's like I'm pushing on it, it won't go. I'm not strong enough. You know, like what do you do next? Some of you maybe are mechanically inclined. Dang, it won't go. What do you do now?
Would you put the wrench on the other side and then hit it with the hammer?
Hit it with a hammer, like more force. Does that make sense? More force. Go get a friend, hit it with a hammer. Like do something that's more force. My muscles aren't big enough, so I'm going to try to do something that gets me more muscle. So hitting it with a hammer.
Get a longer wrench.
Yeah, longer wrench. That's kind of your two options. You need more force or you need a longer wrench. So it turns out torque, or desire to rotate. That's really what that is. That desire to rotate really depends on two things. Certainly your push or your force. But as it turns out, also your lever arm distance right there, where you're pushing. And so there is one of the things you can do if you don't sort of have a longer wrench is what's called a breaker bar over the top of this. Slide like a pipe over the top of it and then kind of move your push out to here. Does that make sense? And so you're actually you might get it to turn now, not because you have any more force than you had a second ago, but entirely because of the length.
Caesar, your mic is not muted.
Thank you for fixing that. So it turns out torque, as you may already know, is force times distance. If you don't, you have a head start on your physics class someday. So you actually get to multiply those together to find out how much desire there is to rotate. And that's why both of those are options for you to increase your torque. If you can't increase your force with a hammer or with a friend, then increase the distance and then it might turn. And so that's kind of cool. So notice one thing that's extremely important here. Note that this calculation is made when the force is perpendicular to the distance. In other words, that push needs to be at 90 degrees. Now, to our point earlier, I'm gonna just make a super rough drawing of this. If this distance here was like 18 inches or something like that, and there's two stupid things you could do if you were trying to get this to turn. One of them is push right here, because although the bar you're using is 18 inches, if you push from right there and that's only 10 inches away, then you're not getting as much torque. The other dumb thing you could do is do this. Do you understand both of those mistakes? Do you understand that this is exactly what we just talked about? So if you push right there with, we'll say 120 pounds of force. Now again, maybe the nut's not that tight, and it'll turn anyway, you know. But you don't get to multiply 120 times 18 here to get the torque. Does that make sense? Because your lever arm isn't 18. You're going to have to multiply 120 times, well, 10 or whatever that is. And then even 120 isn't right. Do you understand that? if you're sitting here pushing at, say, we'll say a 70-degree angle right there, well, actually what you have to do is exactly what we just studied, which is kind of that projection business, or you got to come up with what that angle is. You got to come up with what that is, because this is perpendicular. And so that's actually your force right there, not this. So, and notice what math you do, by the way. If I wanted to find the actual force there, let me draw this figure a little bit better, since if this angle right here is 70 degrees, notice 120 is the actual vector. Like that's the length of the green vector that you're pushing on. And so, you know, great, you're pushing right there at 120. What's the math to find F? Notice it creates a right triangle. Is that a sine, cosine, or tangent problem? You should say, I think you know this, you just don't want to answer because it's boring and easy. The sine is the opposite over the hypotenuse. So basically your force had to be modified by multiplying by the sine of 70 degrees. Notice in our last problem that for the dot product, it was like cosine came up naturally. Whereas this time it's sine that comes up. And so in this problem, your actual torque, we'll say that distance is actually 10 inches. 120 times the sine of 70 is actually I'll say roughly 113. So that's why it's dumb. Like you're wasting some of your pounds. And I notice 70 is, I want to say reasonably close to 90. So, you know, you get a lot of it. Like you didn't waste everything. If you pushed it at like 40-degree angle, you'd really be dumb. But what you're really getting for torque in this case is just force of 113 times the lever arm, actual lever arm distance of 10 inches. So you'd get 1130. And notice the units for that is really weird, because in this case it'd be pound inches. Typically that's measured in foot pounds, so you make your distances be in feet, but basically that's how much desire this thing has to rotate. And so if that's, you know, the nut's too tight, then bummer. But you can appreciate if you moved out to the end and you actually pushed perpendicular, 120 times 18 is 2160, which is like double that. So you're getting double if you actually moved out to the end. And that's the idea. So if you want something to move, you got to push on it, and you got to push a distance away from the center, you know, the place, the center around which it's going to rotate. So this is something that's of great interest. If I'm turning a steering wheel, it's hard. Anything that involves trying to turn something, grabbing the nozzle on a outside of your house to turn the faucet on and so forth, anything you want to turn involves torque. And basically torque is the measurement of, you know, how, as I said, how much desire there is to rotate. So you can appreciate that what I just showed you, though, is, well, two-dimensional. And so, you know, what's this going to look like in 3 dimensions? And so that's kind of what we got to look at now. Let me see. So let's just kind of formalize this a little bit. Kind of conclude, like draw a conclusion from what we just did. Just thinking about how I want to draw this figure. I think I'll just draw it randomly. So if this is vector u, which remember can be anywhere, and we'll say this is vector v, which I, in this case, am going to draw somewhere else. Now, what these two quantities ultimately are going to represent is exactly what we just drew a second ago. In other words, I'll just let u, which I'll redraw here, I'm going to let that represent our distance. In other words, this is the point of rotation right here. And so vector u is actually going to be the distance. So I said force times distance. So that's it's kind of our distance vector. Use our distance vector. And then B, because that's where you're going to kind of push on. Does that make sense? And so this is vector V. And again, I just redrew it in a new location. That's going to be your force. So we're basically conceptualizing the one vector as being a distance and a direction, but mainly the length of it is a distance, whereas the length of the other vector is actually a force. I mean, it's kind of interesting, right? One is feet and the other is pounds. So if torque equals a force times a distance, then our distance, wouldn't our distance be the magnitude of vector u? Isn't that true? It's like how long it is, right? That's what we want it for. That's what we want to do with u, is know how long it is. And so that's what the magnitude does. So I know that now. And then force is force, except for it's got to be perpendicular, right? And it's not right now. So how do we make it perpendicular? Well, we do what we just did. We take the magnitude of vector v, because that would be the length of that vector is a force. Remember, a long vector means big force, so short vector is small force. So we take the magnitude of that, but then we got to modify it by the sine of whatever the angle is. Because the sine of the angle, well, it's sort of perpendicular to it. Does that make sense? So now you might be a little bothered by the angle and so forth, but just to, I think I'm just going to erase this, but does it make sense that it wouldn't hurt anything if I just redrew u horizontally? Because all I need it for is its length. And as long as I maintained whatever this angle is right here and drew vector v kind of going off in that direction and just kind of maintained whatever that angle is. Actually, I don't think I need to erase this. Actually, I should be using a different letter for that angle since I use theta for something else. Call it phi. As long as I maintain that, then vector v over here, its angle is a little clearer. In other words, isn't that theta right there? And so if I take the length of v and multiply this by the sine of it, isn't that kind of our perpendicular force? Isn't that what we just did a second ago? So my point is, without loss of generality, I could rotate it so u looked flat, and then the angle would sort of make more sense. All I'm trying to do is give you a conceptual understanding of this. And so together, that's torque. Like that's what I do. I can conceptualize this with two different vectors. Now, again, the problem with this is when we go to 3D, you don't need cross products to answer these questions if we're in 2D, just like you don't need dot products to find the angle between two vectors if you're in 2D. But when you go to 3D, that little mnemonic device is really kind of cool. And that's kind of what I want to introduce to you now. So this is torque. Ultimately then, I'm just going to kind of write this out. So torque is equal to that statement. Hope you see some logic into that. So I think I'll start this with something 2D. What's a cross product? Where does that come in? How does that come into play? So let's say that our distance, kind of our distance vector, which I'll stick with u. Let's say that's, I'll kind of make it like the picture above, like over 5 up 2. So there's kind of our distance vector. And then our force vector, V, I'm also going to put that at kind of, some, well, kind of a similar angle to before. Let's say it's over 3 up 4. So I said a second ago that, in terms of conceptualizing this, you can kind of pretend that this thing is rotated flat, but let's actually leave it alone. Let's leave it sitting in some weird orientation. So let's draw this. What does that look like? So 5, 2 over 5 up 2 is there. Now, and you could do Pythagorean theorem on that and get the square root of 29. So we know how long that distance is. We understand that. And remember, this is our point of rotation. So there's our distance. And now we got our force vector kind of taken off in a different direction. And that's over 3 up 4. So we're kind of pulling on this. Now, because of the perpendicular thing, do you see why this is kind of a pain? Like this is kind of a problem. But let me show you why vectors are cool. This is just another reason to help understand why vectors are really cool. So would you agree that this is since this is vector v, this is like the y component of vector v? I mean, it's attached right there. Again, think of it as just a rope and you're pulling. So vector v is pulling off in this direction. And notice I drew it the correct length because it was up 4, right? That's a distance of 4. Let's put it in there. And then this vector over here, that's the x component of vector v, and that was a length of 3. And those were already given, like we already knew that. So what we're going to see here is it actually helps to conceptualize all of these things as x's and y's. Well, notice you could do the exact same thing with the distance vector. Isn't this distance right here, that 5 distance right there, isn't that the u vector? The distance vector, that's its x component. Let me think, where do I want to put this? I'll put it right here. And that's the u y component vector right there, which again, we already knew, like those were already given to us. So what I'm saying here is, rather than somehow have this weird distance right here, which is, as we said, like the square root of 29, 5 squared plus 2 squared, that's the square root of 29. And then trying to get v, trying to figure out what version of v goes that direction. Does that make sense? That this is the perpendicular version of v. And so if I had this length and I had this magnitude, that perpendicular version of v's magnitude, then I could multiply those and that would give me the torque, right? The desire to rotate. But can you appreciate the square root of 29 was a little bit of work. And actually the perpendicular version of that, like how to get this vector to be perpendicular to the green vector, that would be a lot of work. Now you may remember, hey, we can probably do that because didn't we say the dot product was a way you could find perpendicular vectors? But doesn't that seem like a lot of work? Maybe we'll do that in a second. But let's do this the easy way. Remember, vectors can move. So we have everything we need sitting in this picture right here to not hardly have to do any work at all. The question is, do you see that? Let's play with this for a second. Do you see that we have a distance of 5 sitting right here? But then look at Vy. So this distance of 5 was actually the x version. I want you to think about what that was. It was the x version of the u vector. And then this red 4 up here, couldn't I just move it to right there? Remember, these vectors can move. If that's a distance of 4, or remember a force of 4, like 4 pounds, and this was a distance of 5, like 5 feet, isn't that already perpendicular right now? So there's 20 foot-pounds of torque right there. But then what else do we have? Don't we also have a distance of 2 vertically? And isn't there perpendicular to that already? If I just move it over, a red vector of 3. Can you see that also working? In other words, that's 3 times 2. That's also perpendicular. So that's another 6 foot-pounds for a grand total of 30. I'm sorry, 26. Where did I get 30? That's the right answer to this question. 30 or 26. How badly does that vector pulling it some weird direction, this pulling in this weird direction right here, how badly does it want to rotate if this is connected by that distance right there? The answer is 26. But I want you to notice, what did we do to get that? We multiplied 4 times 5, and we added 3 times 2. Now, there's one problem with what I wrote. Does anybody know what it is? I did this on purpose this time. A lot of times I'll do this on accident. Are both of those causing the same rotation? Would you agree this one up here is actually causing counterclockwise rotation? Because it matters what direction. Is that the same thing that's happening with the other one?
Oh,
Isn't
so
this one-
should it be 20 minus 6?
Exactly. Do you see how they're actually working against each other? One was trying to go one way and one was going the other. So they're not working together, they're working against each other. So, oops. That's the right answer. And I guess we'd have to make the note that it was counterclockwise, right? Because the 20 was bigger, right? And you know, counterclockwise is called positive. So I could just say positive 14 and that would mean the same thing. You are a mathematician. And so you understand we have a sign addressed to those two types of rotation. But it's kind of cool just to write counterclockwise because then everybody understands it, even non-math people. So these actually worked against each other. Now I want you to stare at these two vectors up here. 5, 2, 3, 4. Those of you in linear algebra and who've had a little math have seen this someplace before, but I'm wondering if it was explained to you in a way that you could really get your hands on. What do I do to these numbers? Like, what's the magic shortcut? Boom, like a dot product. This times this plus this times this. What's the magic shortcut to produce this answer right here? What could I do to those numbers? Like we had a 20 and a 6, but where did the 20 come from? Wasn't it 5 times 4 and 3 times 2? That's why this is called the cross product.
Determinant as well.
Say again?
The determinant of it as well.
That's exactly right. And so if you've had some linear algebra someplace, like that's also called a determinant. Like that little statement right there is a process. The point is that's pretty memorizable. In other words, if you just wrote those two vectors kind of on top of each other like this, and mathematicians will put a box around them like this, which means take the determinant. If you multiply those in a cross pattern, cross product, but then what do you do with those answers? Because you get 20 and 6. You don't add them, you subtract them. And so that's a cool shortcut. So what this illustrates right here, and I guess for those of you that are going to take other math and so forth, what that illustrates right there that's so important is, do you see how easy this problem is if you break vectors into their XY components and you don't talk about the hypotenuse and the angle? Like just leave them 4, 3, just leave them alone. Like this thing is 5, 2, 3, 4. That's the best way to describe a force. Give me its X and its Y, because I can turn that into a magnitude if I need it. And I can inverse tangent 2/5 and turn it into an angle if I need it. But in this particular problem, everything was perpendicular already. And again, this is why perpendicular is so important, because torque is calculated as two things that are perpendicular. And so they were already perpendicular, so just leave them alone. But it's kind of interesting that to get 20, we took the U of X length and we multiplied it by the V of Y length, right? And we took the X of one times the V of the other. Now remember, the dot product was the X of the one times the X of the other, right? And then the Y of one times the Y of the other. It was like X times X, Y times Y. Whereas this is actually the reverse. It's like the X of one times the Y of the other. And then reverse. And then because these were working at cross purposes to each other, we needed a minus sign built into it. And so kind of the takeaway for this of what a
I think we got a black screen.
so you guys can still hear me now, right?
Yeah.
No,
Can't
it's
see
really
you
bad.
though.
Because that's the third time this has happened in class. The computer just kind of blanked, but I don't know why. Everything's powered up. I don't know. Figure it out later. So anyway, we'll go more into that later. But what I want to do really quick is just kind of take this problem over here. Let's see if we can actually get. Let's see if we can actually get this answer the hard way. Actually, I don't know. So I think everybody's happy that this is the square root of 29. That's our distance. But the problem is now is we need this length, because that's a force. So the length would be the perpendicular value. So how are we going to get that? You see what I'm saying? How are we going to figure out what that is? How are we perpendicular? Well, remember this vector was, this was our u, and it was over 5 up 2, right?
Isn't it when you multiply the cross products equal to 0?
Yeah. So we need some other vector, v perpendicular, so that when we dot product those, and again, we're never going to do this. I'm just kind of showing you why this mnemonic device up here, this weird little multiply, diagonal, and subtract trick saves us a whole bunch of work. But I just want to see if we can get the same answer. So we need u dot v, the perpendicular version of v, to be 0, right? Because then that would mean the angle's 90, right? So couldn't I just flip them, like put a 2 here and a 5 here, and then make one of them negative? Wouldn't that be 10 and negative 10? But how do I know it's 2, 5? Like, because there's other possibilities, right? Like if I made it 4, I could make this 4 and this 10, and it would also work because you'd have 20 and 20. Based on the picture, which one of those is negative? Let's just stick with 2, 5 right now. Which one of those is negative based on the picture I just drew?
The X?
Yeah, notice it's like left. Whoa, that was wrong. Notice I'm going left and then up. And so if we're going to match the picture here, then I need this one to be the negative. Now, if you get that backwards and you go to -5, does it make sense the vector is just down here? So it's actually still perpendicular. It's just not going the direction that we want it to go. But is it the right length? You see what I'm saying? What was the length of our original vector? What was the length, the actual length of v? It was 3, 4. So doesn't that mean the magnitude of v, we got kind of lucky here, is 9 plus 16 square rooted. So it's the square root of 25 or 5. So that's length 5. Does that make sense? So the vector v's magnitude is length 5. Are you suffering? Like I'm suffering, trying to figure out like how does this work? This thing's actually going in a direction. I'm just moving that so that it's kind of right on 5, 2.
Yeah, that is tough doing it the other way.
So let's see. 1, 2. It's 3, 4, right? Not 4, 3. So that's actually vector v. That's where v is supposed to be, but we're trying to, reorient it. We're trying to send it in another direction. Well, would you agree this is the right direction? Well, let's use what we just did with projection. Let's use the logic of that. It's got the right direction, but it's not the right length. So right direction, wrong length. But how do we fix that? Well, it's pretty easy to fix actually. What do? Well, we make it a unit vector. So the unit version of this, since that distance is also the square root of 29, the unit version of that would be -2 over the square root of 29 and 5 over the square root of 29. Do you agree with that? So this is now length 1. Well, what do we have to do to make it length 5? You tell me. We talked about this today a little bit, but the question is, are you putting together all the pieces?
You just do a scalar multiple of 5, right?
That's exactly right. All I have to do is multiply it by 5. And I like that you said the word scalar because that's what numbers are. I just need this length 1 vector to be 5 times longer. And incidentally, you future math teachers, everything I'm doing right now is unplanned. I've never tried it before. I'm just like, this is what makes math fun. You're just thinking about it. I'm sure hoping we get 14 for this, but it's, man, these are crazy numbers. So let's see, that means V perpendicular. Let's see, I don't even know what to call it now because I already called that other one V perpendicular. So I'll just say the vector perpendicular to U well, actually, I think I see a conceptual problem with this. Does anybody know what I'm thinking here? So I'm just multiplying 5 in there. And so here's kind of my new vector. So would you agree that this one is, I'm gonna go fast here. This one is now pointing in the correct direction, but it's still length 5. Well, it was this direction that was length 5. Do you understand that? But remember, what we got to do is even worse because we got to project it down onto this over here. You understand that?
Yeah.
I think my screen just went black again. So unfortunately, this is not the vector we need. It's going the right direction, but we actually shouldn't be multiplying it by 5. It's actually, we need to be multiplying it by, well, something that was modified by the sine of an angle, right? So now I'm staring at this going, well, what angle is this? So this would be too long. So how do we get that length? How do I,
Can we use the projections and then like project our V vector onto the perpendicular?
ooh, that's a good idea. Couldn't I project? Can we project our V vector onto our V perpendicular vector? Ooh, I like that. Now remember, the V perpendicular vector was just a vector in the right direction. So I could actually use this vector. I could just use that vector for V, but let's project the V vector onto that. Oh, that's cool. So that, because we're kind of out of time here, I'm going to go a little bit faster since our V vector, I'm just rewriting it down here, was 3, 4. So I'm using these two right here. So the V perpendicular vector is the correct direction. The V vector is the correct length. So we said, okay, we have to dot product those. Notice you get -6 plus 20. Hey, that seems kind of maybe not coincidental. -6 plus 20 is 14. I doubt that's coincidental. And then we divided by the magnitude. Wow, why do I have such a bad memory? Oh, the vector V distance, the magnitude of V squared, which was 5, right? The magnitude of V was 5, but we squared that, so that's 25. And then we just multiplied this by the V vector. There we go, that's what it was. Isn't that true? So I get 42 over 25, which is 1.68. And I get 56 divided by 25, which is 2.24. Did I lose some negative signs? We'll have to pick this up tomorrow, but that's bothering me because notice those two numbers are both positive. Anybody see any mistakes? Those two numbers came out both positive, and yet isn't our vector have a negative x and a positive y? Oh, I know what I did wrong. We're projecting onto v perpendicular, not to v. This is the wrong vector. It's a good mistake to make in the sense that you might make that too, right? Aren't we projecting onto that vector? So I got it wrong. So we get negative 1.12, and we get 70 divided by 25, we get 2.8.
Now will our 25 be different? Our magnitude, because now we're using is it the magnitude of V now that we're using?
Yeah, am I using the wrong one there too? Let's. Projection of u. Yeah, it was supposed to be the other one, right? So that's supposed to be the square root of 29 squared. So it's supposed to be 29. So that was wrong too. Notice that's really close to the same answer, which means if we had checked this on the graph, we might not have caught that mistake. So I get negative 0.97 and 2.41. So that actually looks right now. And so what do we have to do this manually? Well, we know our distance is square root of 29. We just have to come up with the distance or the size of that. So I just have to do Pythagorean theorem on those two numbers. So the magnitude of that would be, I'll just do this really fast because we're out of time, 0.97 squared plus 2.41 squared. I got approximately 2.6. So then the torque is the force of 2.6 times the distance of the square root of 29. Look at that, 13.99. It's rounding. That's the only thing that caused that. So are you convinced that looking at this in terms of vectors is better? So we'll pick it up there tomorrow and look and take this to 3D, because you can appreciate what I just did was possible in 2D, but what if we just tried to do what I just did in 3D? Like there's
You can't do cross product in third dimension.
You can actually, it turns out. I'll show you. Very good
Oh,
point
yeah,
though.
yeah.
Very good
It's a
point.
little bit, it's more though. It's gonna be a
Yeah,
little harder.
right. Nice job. It's really weird. It's so this was a 2x2 matrix. So it is possible to do this, well, kind of manually, but even then, didn't we end up using like dot products and some of the mnemonic devices we chose? And I'm sure we could speed that process up. I'm sure we could automate that a little bit, what we just did kind of the hard way. But it sure worked easier just with what we did right here, didn't it? I got 14 way easier. All right, get on out of here and I'll see you guys tomorrow.
All right, thank you.
Thanks, Doug.
you tomorrow.
See you tomorrow.